I want to start out today's class going back to something that's usually beginning of the semester, but it doesn't really make sense until now. So we're going to talk about states of matter, solid, liquid, gas. And I want you thinking about any particular substance. Actually, let's talk specifically about water. So we have water molecules. What defines it as being water? Say it again.
2 hydrogens, 1 oxygen.
And what about them?
They're bonded together.
Okay. So the really big thing that defines water as being water is that you have 2 hydrogens bonded to 1 oxygen. Remember, just like if we go back to defining what makes hydrogen hydrogen, it's that it has 1 proton. So there's certain things that make water water. So I want us thinking about if we have water that's a solid, do we have a special name for that? If we have it as a gas, do we have a special name for that?
Steam.
All right, so we have steam and we have ice. Mist is, yes, one of the versions of water. I don't know if it's technically a gas. It's kind of liquid form, but it's floating in the air. If we have this, is that still water?
No.
So I have had a lot of very smart people tell me that when water boils, we end up with hydrogen gas and oxygen gas. Why is that not possible? Talk to your neighbor for a second. Why does it not make logical sense that if we boil water, we end up with this? Can you? Yeah. So Gail. I'm not sure who the others are right now. Okay, so can we hear one description? Can I get a hand raised? Why is it that that is not a possible description of boiling of water? Neighbor?
A chemical reaction doesn't occur, a physical reaction does.
Fantastic. So I want us thinking about chemical versus physical reactions. A chemical reaction is one where the bonds break, where we no longer have the same connections between hydrogens and oxygens. We now have different connections. We have hydrogens to hydrogens, oxygens to oxygens. That is a chemical reaction. There's another categorization of reactions too. We talked about nuclear, where an oxygen might change to another nucleus. That is a different category yet. So today we're going to be talking about changes of state, how it is that individual molecules will change based on temperature, and what that means about how gases interact. We have to picture the molecules themselves in order for this to work. All right, so go ahead and talk to your neighbor for each of these 3. Determine if these statements are true or false, thinking about the water molecule, what it looks like in each of those different states. Should be question 1 on your worksheet as well, if you want to see. I think we have an ABC there. 1, 2, 3. All right, let's go through these one at a time. Let's start with number 1. True or false? An example of solid water, the molecules are not moving. True or false? Go ahead and click in your response, please. How many we got today? We got 40? All right. You know I love simulations.
Yeah.
Simulations are amazing because they get us to look at things at a level that we can't necessarily see, but we can simulate them. So with this one, we have a majority of class saying that this is false. The sample water molecules are not moving. Can I have someone describe what they mean by that? I want to hear from a lot of different people today, so please just volunteer your thoughts. Go ahead, Love.
I guess whether the molecules really depend on the temperature. So if it's usually minus 32, if it's 30 degrees or less, it's frozen and in solids, but that still has energy. And if it still has energy, they're still moving.
Okay, so what kind of movement are we talking about? Can I get into the volunteer? What type of movement might we have in a solid? Almost everyone said there's still movement. What kind of movement? Kiana? Great. So if we have this simulation, I think this does a pretty good job of showing movement. It's exaggerated in that we're zoomed in so far, we're looking at individual water molecules. In this isolated container, we have the temperature. Is that frozen or above freezing or below freezing? What's freezing point in Kelvin? 273 Kelvin is freezing, so that's below freezing. So like Kiana said, there's still movement in those molecules, but those molecules are not moving past each other. They're vibrating. And how are they oriented compared to each other? You guys notice anything about their orientation? So they're having that intermolecular force we talked about because of the dipoles between the hydrogens and oxygens. And so most of the time they're moving like this. Sometimes they have enough energy where they move and they kind of go, maybe they're attracted to another one. But for the most part, they're pointed at another hydrogen to oxygen in that kind of fashion. So then what happens, talk to your neighbor, what would change about this if we then said this is a liquid? If we added heat to it, we brought it up above the freezing point, what would be different about that image? Okay, and when you're answering that question, use logic. You guys have seen solid water, you've seen liquid water. Make sure your answer isn't totally irrelevant when it comes to what you've observed. I heard some comments that might not fit with what you've actually seen. So check and make sure that your answer makes sense. So one of the things, you guys are super quiet still, one of the things I heard is that they're going to be moving and bouncing off of the walls. Is that true, and in what capacity is that true?
When we were doing the homework last night, when it said bouncing against the walls, that was more like gas form, when they like bounce against each other. For liquid, it's more of like they're just kind of like sliding.
Okay, well, so there's a qualification, right? If we then go to liquid, are they closer together or further apart, by the way?
Close?
There's less space between them. They're closer together. They're being pulled by gravity now, so they're being pulled down. We'll get to that. All right, so two things. You know that when water freezes, it expands. It bursts pipes. It makes potholes, all kinds of stuff. That's because now these things have a little bit more kinetic energy. Thermal energy, kinetic energy, whatever you want to call it. So they were vibrating. We made them vibrate even more, and we break them. And then they move past each other. That rolls pretty well. They now have enough energy where they're not going to hold on to those intermolecular forces because they're not as sedentary, that now you're going to see them sliding past each other. They're going to bounce off a wall, bounce off another water molecule, but now there's movement to them. They're moving faster. Are all of them moving at the same speed? Is any one moving faster than the other? So what I want us thinking about, if you ever played billiards or pool, you can put a certain amount of energy into the system. That energy will be distributed between all the balls on the table, right? When you break the billiards, then all the balls spread out. It's easy to say, well, it's a certain temperature, so all the molecules are moving the same speed, all the balls are moving the same speed. That's not true, right? If you ever play pool, you look and you see some balls are moving really fast, other ones are staying still. That's the same thing that happens with any mixture of molecules. So even while the temperature of this is not enough for the average to be a gas, right? It's at 50 degrees Celsius. That's like just over body temperature. There's still a few molecules that are going fast enough to overcome those intermolecular forces and become a gas. So then what's it going to look like when we have all of them at a gas? When we're over 100 degrees Celsius or 373 Kelvin? Talk to your neighbor. What's going to be different about that image when we heat it up past the boiling point? All right, I want to hear from a new voice, please. Eric?
They'll be moving too fast for intermolecular forces to really stop them, so they'll just kind of slide right past each
And the other way to do that is maybe I should do this instead. You can heat this up. So now we're putting a whole bunch more thermal energy in, which is becoming kinetic energy for those molecules. Now they're going to move faster and faster and faster. And you can start to see the speed increases. When the speed increases enough for them to overcome that attraction with the other molecules, then they start to float out into space. It's going to take a minute, but now we're over the boiling point, and so if we were given enough time, it would look like that. So all of those molecules are now moving around. Are they all moving at the same speed? Some of them are spinning a lot, some of them are bouncing at high speeds, other ones are almost standing still, some of them are moving really quickly. So the average energy for that system is increased. The average speed is increased to the point where now there's no longer liquid. But that doesn't mean that every single one is. So you go outside in a cold day, a puddle's there in the morning, it's not in the afternoon. Does that mean that we reached 100 degrees Celsius? So let's think about how that actually applies to everyday life. All right, so now that we have kind of this molecular picture of gases, we're going to go ahead and do a whole bunch of other stuff in class related to that. So my view, one of my main take-homes for gas laws is for you to visualize the difference in interaction between solids, liquids, and gases, and then to use that to think about the molecular perspective of gases, and specifically pressure. And we're all going to do that using this molecular terminology. We're thinking about the molecules. What are they doing? If we have a different molecule, how does that influence things? If we have a different temperature, how does that influence things? A different container, all those things. We're going to talk a bit about where gas is going to flow based on differences in temperature and pressure and in the number of molecules. And then we're going to use that to talk a little bit about respiration today. And then on Monday we'll talk about gas laws in terms of weather patterns. So let's step back to a little bit of a calculation standpoint. Standard temperature and pressure. You're going to see that a lot when you talk about gas laws. Next week your lab starting is gas laws. So standard temperature and pressure is 1 atmosphere. How does that compare to what we have right now? Is that higher or less than what the pressure is in this room, probably?
Very similar.
Very similar. 1 atmosphere is kind of like the standardized sea level pressure. We might have a little bit less pressure because we're a little bit above sea level, but it's not going to be much of a difference. 0 degrees Celsius is not room temperature, it's 0 degrees Celsius. When we do our calculations, are we going to use Celsius?
No.
Everything is related to Kelvin. One of the things I forgot to show in this simulation is if we do a solid, at what point will the molecules no longer have any motion? Can we stop all motion in these molecules? I disagree. We can't. The definition of absolute zero is the point at which there is no movement in any molecules. So I don't know if I can actually select. Can't go down to 0, but you see how much slower they are now? And if we were to go all the way down to absolute 0, which I don't think theoretically, physically has ever been reached, I think we've gotten down to like maybe 0.7 Kelvin is the coldest we've ever actually been able to get a system to study it. But we know theoretically exists because you can actually plot the movement of molecules and see how much they're moving at different temperatures, and you can plot the point at which they would reach 0 movement. And so there's a theoretical 0 temperature at which everything stops moving. All right, here's a crazy number to wrap your head around. Have you guys seen this number before? 1 mole of gas occupies 22.414 liters. Okay, easy, I can memorize that. What does it actually mean? If I have a mole of fluorine gas, or nitrogen gas, or oxygen gas, or xenon gas, if I have 1 mole of it at standard temperature and pressure, it always occupies the same volume. That should hurt your head a little bit, because there's so many differences between those molecules, the weight of them, the size of them, the speed of them, all these different things, but they occupy the same volume. That's a calculation we're going to end up using a lot when we're talking about gas laws. So if we know the volume of a particular gas, and it's a standard temperature and pressure, we can figure out how many molecules are in that. That's the conversion factor we're going to use. So I want you guys to go ahead and calculate R at standard temperature and pressure. I'll give you guys 1 minute. Calculate it. Use the information you have here to calculate what R is. I'll give you a hint. Use the ideal gas law. Write out the ideal gas law if you're not sure where to go. Look at what you have known, what you don't know. And R is not your known right now. All right, what's the ideal gas law? Savannah, what's the ideal gas law?
PV equals nRT, so pressure volume equals number of molecules times R times
Number of moles, careful.
moles, times R times temperature in Kelvin.
Great. So we have our ideal gas law. Can we rearrange this to solve for R? All right. So we divide both sides by NT. So we have R equals the pressure of a system times the volume divided by the number of moles times the temperature in Kelvin. All right. Units are extremely important. Can we use pressure in different units than atmospheres?
Yes.
And this one is probably easier to do atmospheres because that's what's given for standard temperature and pressure. If we were using millimeters of mercury, it would be 760 millimeters of mercury, and then we'd have a different gas constant. The ratio is still the same. It's just we can use different units for our, pressure. All right, so what is our pressure is 1 atmosphere. What's our volume we're going to use in this case? We're talking about 1 mole of gas is an easy one to start with. So 22.414 liters. What's our N? 1 mole. Temperature? 0 degrees Celsius? All right. So if we put all of those things in, that's where this gas constant comes from. You guys used it, and I don't want you just using a number that you don't realize is something that actually comes from looking at the relationship. If any of these change, that gas constant will stay the same for an ideal gas, and it will just influence, if one of these changes, the volume changes, then the number of moles will change. Or if we change the pressure, then something else has to change on the top and the bottom of this in order for that ratio to still be held constant. So mathematically, that's what I want you guys thinking about. So let's go back. This is the question I asked at the end of last class. We're going to be thinking about the molecular view of gases that we showed in the beginning of class. So which one of these is the most accurate description of how we measure pressure? Go ahead and click in your answer. I want you thinking of a gas pressure sensor that we put into a system of gas. So your car tire pressure gauge. Force over area. So with this question, I'm trying to get us honing in on looking at the molecular perspective. We have these molecules of gas that are bouncing around. It could be water, it could be nitrogen, it could be anything, right? The way that we're measuring pressure is, in essence, we're taking a small area of the side, and we're seeing how much force is applied to that over a set period of time, right? It's an average over time. So every time a molecule hits, we're going to feel some force against the side of it. That's how we measure pressure. What happens if this molecule that hits moves slower? Is that more or less pressure? So if we have the same molecule hit fast, it's going to be a lot of force. Slow, it's going to be less force. So that means that our pressure is directly correlated to the speed of the molecule. What about if it's a heavier molecule? What if we were to use xenon and that were to hit at the same speed? If those two hit my hand at the same speed, which one would generate more pressure? Xenon that's heavier or water that's lighter? Why would it be xenon?
Maybe you get hit by a pickup truck and you get hit by a Volkswagen.
Who wants to get hit by a Volkswagen? Yeah, so if you think about if they're traveling at the same speed, if you get hit by a bicycle versus if you get hit by a truck, there's going to be a big difference in the force, which is how we're measuring pressure. I don't know if you ever thought about gases this way. When you measure the tire pressure in your car, literally it's gas molecules that are hitting that sensor, and depending on how many of them there are, how fast they're going, that's going to tell you what the pressure is inside your tire. It's actually pushing back on a little lever, if you will, inside there. There's a membrane that pushes back.
Why is it usually nitrogen?
In your car tires?
Yeah.
So it's usually air, but you can pay extra for nitrogen because
When it heats up, it doesn't expand or contract as much as regular air does. No?
nope.
Oh, they lied to me then.
That's all a measurement of how many molecules are there. That's it. It's in theory less of them escape, I believe, a fusion. So it's about the size of the molecules. So I don't know that I buy that. I need to go do some more research. Maybe you guys can do the research on that and come back and talk about it on Monday, because conceptually that doesn't make any sense. Conceptually they're less likely to diffuse out of the tire doesn't make sense because nitrogen is smaller than oxygen, which is what 20% of the air is.
I'm just kind of curious, how are we defining an ideal gas?
So an ideal gas is one that behaves exactly by that equation we just looked at, which is most gases at room temperature. Once we get really hot or really cold or really high pressure, they don't act that way. They act very differently. Good question. All right. So we're talking about how the gas collides with the outside of the container, whatever it is we're measuring the pressure of. So then if we go ahead and ask the next question, when the temperature is raised, what happens to the pressure? I want you to describe this in a molecular way. There's a space on your paper to write down why from a molecular perspective. So now I have a picture of the molecular view. Go ahead and write down your thoughts on if pressure would increase, decrease, or not change, and what the molecular justification for that is. All right, we've got 29 votes.
Oh.
Savannah, can I hear your response and your thoughts? Why did you say pressure will increase? What's the molecular justification for that?
Because the atoms are moving faster.
The molecules or atoms depends on what the gas is, right? So the particles are moving faster. So then why does that result in a higher pressure?
Because, like how we just answered the last one, they would be colliding more with like the side of the container, if you're having that inside of the container.
Great. So I love, there's two parts of the reason why. And you answered the less obvious one, which is great. When they're moving faster, it means they're going to have more collisions per second, whatever time unit you want to use, right? So if we put my hand here, it used to hit, I don't know, once every 2 seconds or something like that, and now they're hitting 2 or 3 times per second. What's the other reason that's sometimes more intuitive? Why is the pressure going up when they're moving faster, DeAndre? Okay, so based on the equation, yes, as well. And Trey?
Force is mass times acceleration, so it'll increase the force if the acceleration increases as well.
Yeah, so as their speed increases, you're going to have more of an acceleration when it changes direction. So going back to F equals ma. But that force that you're going to feel at every point, because they're going faster, is going to get higher. So it's really 2 points. It's that you have a harder collision for each molecule, and you have more frequent collisions from those molecules. Is this how you usually think about pressure? Just want to make sure that we're not boring you guys with stuff you've already thought about. So then let's think about, well, what if we expand that balloon then? What if it's at 35 degrees, but we expand the balloon now? We give it more room for those molecules to move. What's going to happen to pressure? And I want your justification for why on the molecular perspective again. Go ahead and answer that. That's question 5.
Are we answering what you're asking us there? Or?
So question 5 is what happens when we, isn't what we,
It's 4 right here.
They're never in order. They always jump around.
question number 5 is if the volume is increased, what will happen to the pressure in the system?
Well, it says if the volume is increased.
Volume is increased. We're good?
You're answering
This is 4.
look on the never on your screen.
Oh, is it not? Did I not reset the clicker?
Well, it says question 4, but
Oh, I see.
it's
Yeah, the 4th question by clicker is question 5 on your worksheet. All right. I want to hear from a new voice. You want to share your answer to this or question?
The other one.
Huh?
So, the nitrogen thing. So you were right, nitrogen is bigger, it doesn't go through the tire as easy as gas does, but regular gas holds moisture. So as the temperature rises and lowers, at extreme temperature, not your car, but as
So if you're on a racetrack, then it
if
matters
you're
more.
a race car, and they use nitrogen because as you get hotter, it expands more and
Expands less probably, right?
That's what I meant.
Huh,
Expands
interesting.
less than tire. So.
Okay. Thanks. All right, so let's have a new voice to help answer this. I want to hear from people who have been quiet. Go ahead, Amber.
First off, just looking at the formula, volume does not affect pressure, so I say it's going to stay the same. And also, the temperature is still constant. We didn't change the temperature of that said volume,
So this is great. This is actually one of the most challenging things about the ideal gas law, is that you look at the equation and you're like, there's 4 variables. Like, what are we changing and what stays the same? So let's talk really specifically about what changes and what stays the same. If we have this balloon filled with gas, and we just expand the walls of that, what's going to change? Are the number of moles of gas inside going to change? It's closed, so that's not going to change. Did the temperature change? In this scenario, I'm saying the temperature doesn't change. Did the volume change? Yes. And the gas constant is the gas constant, so that's a constant. So what else has to change in order mathematically for that gas constant to still be a gas constant? The pressure. So the pressure does have to change in that system. Something has to give. So if it was a real-life scenario, the pressure and the temperature would probably change. But we're kind of doing an artificial thing where we say that we're still setting the thermostat at the same temperature. So what would happen to the pressure inside that balloon if we expanded it from a molecular perspective? Kyle?
It decreases. The pressure will decrease.
Why?
Because they're inverses. So whenever the area is bigger for the gas to move around in, you divide force divided by area. The denominator got bigger, so you get a smaller number.
Great. So I love that you're going not to the ideal gas law, you're using this equation. You're saying that the area now, where the same number of gas molecules collides, the area of the inside of the balloon is bigger. And so we're going to have less frequent collisions within that, and so that means the pressure is going to go down. What's another justification? Angel, I saw you raising your hand.
There's more room for the molecules to bounce around.
Okay, great. And so how does that influence the pressure?
It decreases
Why?
because they're not hitting the walls as frequently.
Great. So going back to the frequency of hitting, so you said that the number of them in a square, in an area, is going to be less. There's actually more time in between them colliding. Are there any additional reasons we can use to justify?
I actually did use the ideal gas law, and like if you're just solving for pressure and you divide by volume, that would make them inversely related.
Absolutely. Yeah. So a lot of different reasons to justify that mathematically, conceptually. So I want you to be able to do both. So if we expand the volume, I think I have a little animation to do that, right? So now those molecules are moving the same speed because it's still the same temperature, but now there's further to go between hitting the walls, and the wall surface area is bigger, so you're going to have less force in each area, which means less pressure. Awesome. So let's take that and let's expand it. Let's think about atmospheric pressure. If you're swimming in a pool and you dive down to the bottom of the pool, what's the physical sensation that you have? Why do your ears pop when you go to the bottom of the pool?
More pressure.
What do you mean more pressure?
Well, the pressure down there is higher than the atmospheric pressure that you experience outside of the pool.
True. So I want you to talk to your neighbor for a second and try to think about how our atmosphere here, with all the gas molecules that we can move around, right? You can feel them when you move your hand, the hairs in the back of your hand, you can feel the gas. So those things that we're pushing out of the way, how does that relate to why our ears feel pressure at the bottom of a pool? What are the similarities between those two scenarios? If you've been in an airplane, when you're up high in an airplane, when you come down, your ears will feel the same pressure. What is that about? Think about the ear pressure at the top of the pool is not necessarily about the time. Why? All right, so I want to have Gail say what he just said again. If we go down, you said a certain depth, then we have basically twice atmospheric pressure in our ears because that air is getting compressed. Why?
Because of the weight of the water.
Okay, what does that mean, the weight of the water?
It's more dense than the air. So
Well, it's more dense in the air, which is why it's in the pool or the ocean and on the air. It's closer together, it's denser, things go down. Why is it, where does that weight come from? Gravity and the molecules of mass. Alright? Does air succumb to the same principles? We say no, we say yes. I want to hear why. Amber?
Because as you go higher in elevation, at the atmosphere, the pressure actually decreases.
Why?
Because the air is thinner. There are
Why?
less molecules in the air as you increase in elevation.
Have you guys ever thought about pressure this way? It blew my mind the first time I thought about it. We are under a sea of air. They have nucleuses, right? We have CO2, oxygen, nitrogen molecules. They have mass. We have gravity. So here we have a lot more of that mass over the top of us, just like the bottom of a swimming pool. It's a lot less dense than water, but it still has density. You can take a helium balloon, less density, that goes up. That shows that we have all this air that has density around us at all times. So if you think about, I wish this were moved over here to Arkansas, right? We are at the bottom here. Above every single one of us, you can imagine that there's kind of a column of air being pulled down. Air has mass. Gravity is pulling it down. There's a little bit less gravitational pull out here. But overall, it's the amount of air that's over us that pushes down, and that's what makes atmospheric pressure. So if we go up on top of a mountain, are we going to have more or less pressure on us, and why? Why is it going to be less? If you go to the top of Mount Everest, it's literally a third of the pressure. Does that blow your mind? A third of the pressure. It's a huge difference. That means that there's, whenever you take a breath, you have a third the amount of molecules going into your lungs, because now they're spread out much more.
Is it because you're further away from gravitational pull?
So the gravity isn't going to change very much. If you think about from the center of the Earth to the surface of the Earth versus the top of Everest, there's a very small distance change. But the atmosphere is incredibly thin around the Earth. And so we're going much higher towards the surface of the pool in that scenario. We're going, I don't know.
What keeps it closer to the surface?
Gravity.
Instead of the top? But you said it was like a minuscule difference.
No, I'm saying that gravity, if we're at the top of Everest, we're not going to be able to measure much of a difference in gravity. But the atmosphere, there's only so much gas, and so it gets pulled within a certain distance of the Earth. And if we go up towards the middle of that pocket of air, then we're going to have much less air we breathe in. Kind of like if you go halfway down the swimming pool versus to the bottom. And actually, if you've ever seen a barometer, the way that they work is fascinating. This is a mercury barometer. You have a bowl that just has mercury in it. Mercury's super dense, right? It's a liquid metal, but it's super dense. It pushes down. You put a tube in there. The tube, you literally move all molecules. Complete vacuum. Nothing inside of it. You put that down, you release the vacuum. Why does mercury go up inside the tube? What's the reason the mercury goes up inside that tube?
There's the pressure difference between the outside air and that vacuum.
So what's forcing it up?
Well, there's no pressure in the vacuum, so the pressure from the outside is forcing it up.
Okay, and what I want to try to get us to think about is there's actually nothing pulling inside. It's actually atmospheric pressure pushing down on the mercury, and the only place that's not pushing back is inside the tube. So atmospheric pressure, literally gravity pulling down on the air molecules, pushes that back up. Kind of a different way to think about gases and pressure. All right, you guys went through in your pre-class quiz. You can describe pressure in a whole bunch of different units. Just be really careful with your units. When we calculated R, we could have used millimeters of mercury. We could have used bar. We could have used torr. We could have used PSI. We could have used any of those, and we would have had a different numeric value for R. So whenever you use R, make sure that it matches the units that you have in your calculations. It doesn't mean that there's a different relationship. It just means we're using different units.
Are we going to have to memorize this?
Nope, you have to be able to use. So on an exam, I would give you this table. And you need to know how to convert between units or to use the appropriate value of R. All right, let's watch a little video. Did I just hear someone complain that we have to watch a video? Or did Gail just hit his knee? Let's see if this works.
Hey, it's me, Destiny. Welcome back to part of the rocket van, and I've got two little science helpers here, right? Are you wearing your seatbelts? Yes. Okay, we're going to do something pretty interesting. Check this out. I've got a pendulum suspended from the top of our family van, and we're just going to drive forward. We're going to accelerate. So if we're going that way, which direction do you think this pendulum should go? What do you think? 3, 2, 1, go.
Yes.
Which way is it going?
My way.
That's right. It's because I'm accelerating, right? Does that make sense to you guys?
Yes, sir.
Okay, very good. I was hoping it would make sense. So we're going to change it up just a little bit. Okay, so now what I'm going to do is I'm going to replace this pendulum with a balloon. We should see the same thing, right? We cut this off. So what we're going to do is we're going to accelerate that way. So we have the mass of the balloon and the acceleration, so that should net in a force, and we'll have to react with this string, right? You guys ready?
Yeah.
What do you think is going to happen? Talk to your neighbor. What do you predict is going to happen to the balloon? And why? All right, let's do a quick vote. The balloon will stay in place. It will not move forward or backwards. The balloon will move backwards because acceleration. The balloon will move forwards because life is crazy. All right, let's check it out.
3, 2, 1, go. Wait a second. What just happened? Oh, why did I stop? The balloon goes backwards when I stop.
Why? Someone raised their hand and predicted that. Why?
Because the air inside the balloon is less dense
Then
than the atmosphere inside the van. So as the atmosphere inside the van moves to the rear as the van moves forward, the less dense air inside the balloon is going to still go to the area of less density in the atmosphere.
What's happening?
It's staying the same.
3, 2, 1, go. There it is. It's coming right at me. Why is it doing that? Do you want to know? I brought something to show you. Remember I told you I was going to bring this jar earlier? Remember that? So it's like this. Imagine this entire van is just like this jar. And all the air inside this van is just like the water in the jar. Does that make sense? So let's imagine that the balloon is this bubble on top. Because the helium in the balloon is lighter than air, right? So that causes it to do what?
Go up.
Go up, that's right. So if I've got this air that's just like it, what happens if I move the jar that way? All that water sloshes to the back. And when that water sloshes back this way, which direction does the bubble go? You see that? So the air bubble moves in the direction of acceleration. Does that make sense? I know you're 5, but I think you can get this. Okay, so I got my seatbelt on. If I drive forward real fast right now, which direction is the balloon going to go?
Forward.
Why will it go forward?
Because all the air is splashing back.
That's right. Very good. Watch this. Look at that. You see that? So you know what that means, don't you? That means you have more air to breathe than Daddy does when I'm going fast. Did you?
All right. Hopefully I'm giving you guys some different perspective on gases than you've had before. On a daily basis, I don't think that we think about gases having mass. And so if you can isolate different densities of gases, I think it's a really interesting perspective. So let's talk about breathing. I want you focusing on the 2 arrows on each diagram. Skeletor on the left, chest is expanding when the diaphragm contracts. On the right, the chest is contracting. So which is Skeletor exhaling? And then think about a molecular explanation for why those 2 arrows on that diagram would result in exhaling. All right, talk to your neighbor. What's your molecular explanation for why that image would result in air being exhaled? Talk to your neighbor, please. Like. All right. Sam, can you share your discussion on this? Which of these shows Skeletor exhaling, and then from the molecular perspective, why would that result? Okay, why? When the chest contracts and the diaphragm relaxes, that is exhaling. Why, on a molecular perspective, would that result?
Is that like the volume of the lungs or whatever would be less, so the air would be coming out, I guess.
Okay, so we're partway there. Can we add some more molecular description of that? Jason?
The pressure inside the lungs is higher than the pressure outside the body.
Why?
Because the muscles contracting.
Okay.
And decreasing the volume.
Okay, so how does that, what's the molecular component to that we need to add? So we're saying that the volume decreases. Why does the pressure go up?
You're decreasing the surface area of the lungs.
So we're decreasing the surface area of the lungs that we talked about before.
And causing more collisions per second.
There's more collisions per second in the lungs. The temperature didn't change, right? But the volume did, meaning the pressure goes up. And if the pressure goes up inside the lungs, then at the opening, where you have a difference in pressure, lower pressure now, higher pressure, the air is going to flow out. I agree. You guys actually remember Skeletor? Anyone? Old enough for that? Okay, so let me ask the question a little bit differently. So if Skeletor's nose and mouth are closed, when he tries to inhale, what happens to the pressure inside of his lungs? You're welcome to ping a neighbor if you want. Try it. We have a split. We have almost a split answer between all three, actually. So try it. Close your nose and mouth. Try inhaling. Think about the pressure in your lungs, and think about what those gas molecules are doing. Do you think that pressure inside your lungs is going to be greater than atmospheric, less than, or equal to? Go ahead and submit your answer, your final answer, if you have changed. And one of the biggest things that'll help you answer this is we try that, right? And then release it and see where the air goes. Why does that happen? Aaron? What does it mean creating a vacuum? Great. So this is one of the biggest terms that I struggle with in the beginning. What is a vacuum? I initially thought, I didn't really think about what a vacuum was in a molecular perspective. But a vacuum is just anything less pressure than what's around it. So a vacuum cleaner, it just creates an area with a little bit less pressure. That means that the flow of air is into the area of less pressure. It contracts, wait, do I have the wrong picture here? Is that why it's super confusing? I think I showed the opposite picture. So yeah, so your diaphragm relaxes, your chest expands.
Your diaphragm relaxes.
No.
And your chest contracts. Because the way the diaphragm works is kind of weird. It's like awkward. But when it relaxes, your lungs contract, which means that the pressure increases, so it kind of equalizes if you already have that vacuum.
So in this case, if we try to breathe in, plug our nose and mouth, we generate lower pressure inside of our lungs. When we open our mouth and nose, you can hear that air whoosh in. What's crazy about this is if we go and look at how big the difference is in pressure. Remember I said we can use atmosphere, we can use millimeters of mercury, a number of different measurements for air pressure. So if we're using millimeters of mercury, atmospheric pressure is 760 millimeters of torr. It's the same as 1 atmosphere. The difference is only 3/760ths. You put your finger in front of your mouth, feel when you breathe, you can actually feel the force of the air molecules moving forwards and backwards. And that's only from a 3/760th of a difference in pressure. So think about going to the top of Everest, and that would be 30% difference, or no, 60% less pressure in one place than the other. So it's amazing how little a difference in pressure actually makes in our bodies. So I think we are out of time. What I wanted to do was to set the conceptual framework so that when you're thinking about gas laws, you get out of the calculation mindset. Calculations support everything we just talked about today, But I want you thinking about what's happening molecularly when we're doing those calculations in lab next week. Have a good weekend. If you have any questions about your exam wrapper, let me know. If you don't have your exam wrapper, please come see me ASAP. Set up a time if you can't come now.